So we've discussed the different types of electromagnetic radiation, which is really just photons with different energies and corresponding wavelengths. So gamma rays have very high energy, and then as we go to lower energies, to X-rays, to UV, to visible, or even lower down to infrared, microwaves, and radio waves. However, we are talking about the energy of one photon. It's the energy that is gained when one photon of this electromagnetic radiation is absorbed. The intensity of the electromagnetic radiation is also important. The intensity is the power of the electromagnetic radiation that is applied to a surface per the surface area of that surface. So the units for intensity is watts per square meter, which should make sense because our unit of power is watts and per area, so the area is in square meters. So basically, the brighter the light, the larger the intensity. A good example is the power from the sun. So how much power per surface area hits the Earth? Well, the intensity of the sun at the Earth is the total power of the sun divided by the surface area of a sphere that has a radius of the distance from the sun to the Earth. So we can calculate the intensity. The power of the sun is 3.84 times 10 to the 26 watts. Then we divide it by a surface area of a sphere, which is 4 pi r squared. So we divide that power of the sun and divide it by 4 by pi and 150 times 10 to the 11th meters squared, because we want to have our units in meters. So we do that, and we get the intensity to be roughly 1,370 watts per square meter. So the idea is that if we take all the power streaming out of the sun and divide it by the surface area of that sphere, so that power is distributed evenly over the surface, and it gives us our intensity. This 1,370 watts per square meter is outside the Earth's atmosphere, so the ozone layer and the atmosphere and the clouds are going to reflect or absorb some of this energy, so all of it won't make it to the Earth's surface. This number is very important for solar energy because it tells you what is the maximum power you can get for a certain sized solar cell. You can't get more power per surface area than what you get from the sun. So what happens if we go to Mars? Well, at Mars, we're a lot further from the sun, so that means that the intensity should be lower. This checks out because if our distance from the sun is larger, then the surface area of a sphere centered at the sun with the radius going to Mars is much, much larger, so that surface area will be larger, and so the intensity will be much lower. In the next case, we want to quantitatively consider the effect of changing the distance of a planet on the intensity of the light. So the intensity depends on the power of the star divided by the area of the sphere of that distance from the star. So the power will not change. It's the same star, right? So the power is the same. The thing that changes is the radius. Notice the intensity is related to the inverse square of the distance. So if you double the distance, then your intensity will decrease since you're further away, and it will decrease by a factor of 4. So the radius is doubled, so you square 2. 2 times 2 is 4, so it's 4 times smaller. So in the problem here, we have a planet with an intensity of 200 watts per square meter, and we want to know what the intensity is at a planet that is 5 times further away. So the distance of the inner planet is r, and the outer planet is 5r. So yeah, it's 5 times further away. So we use our formula here that the intensity inner over intensity outer is equal to the radius outer squared divided by the radius inner squared. If we plug this in, we get that the intensity outer, what we're trying to find, divided by 200 watts per square meter, the inner power is equal to the inner distance squared, which is r squared, and the outer distance, which is 5r squared. So we rearrange, and we get that 200 watts per square meter r squared divided by 25r squared is equal to the outer intensity. So the r squares cancel, and we get 200 divided by 25 and get 8 watts per square meter. We could also just do it more intuitively. So we are traveling out 5 times further away, so the intensity is inversely proportional to the square of the distance. So 5 times 5 is 25, so you would then divide by 25 because the intensity is decreased. So you do 200 by 25 to get the 8 watts per meter squared. Either way works here. Okay, so you have a question to do, and next we're going to look at the energy density of electromagnetic radiation. Good luck.